Welcome. So, last class we are discussing about vector space. I tried to give you a brief introduction about what is a vector space and mainly discussed on the definition of a vector space and tried to explain it in with a perspective of a real coordinate space. And we saw that vector spaces has certain dimension which or the real coordinate space has certain dimension which is given as R n, where n is the number of components of a vector in that particular space. But R n or a real coordinate space spans the entire space with that particular dimension. Now, we are interested in subspaces or the smaller spaces inside that real coordinate space, in which our solution of x is equal to b will lie in case there are infinite solutions. That is the main motivation for us to look into the particular linear algebra chapter called vector space. So, we came into the definition of a subspace of a vector space. Subspace is a smaller space inside a vector space which satisfies the requirements of a vector space. That is, if we take two vectors in that particular subspace, we add them, they will be in that particular subspace. If we multiply a vector with some constant, that will also lie on that particular subspace. So, the definition can be followed up in that way, that if we add any vector x with another vector y, in both are lying in the subspace, x plus y should also lie in the subspace. We have to see how does it happen, but it happens. And if we multiply any vector x with any scalar c, c x will also be in the subspace. So, it becomes probably little more restrictive than the vector space definition, because vector space or the real coordinate space definition, because real coordinate space ensures that any vector with number of components same as the dimension of real vector coordinate space must be a member of real coordinate space or the largest vector space we can think of in that particular dimension. However, when we are talking to subspace, in that real coordinate space we have narrowed down a particular regime and telling that all vectors belonging to that regime can be linearly combined with each other. In a sense, they can be added to each other or can be multiplied by a constant. One vector can be multiplied by a constant or magnified, and these linear combinations will also stay on that particular subspace. So, we will see how does it work. For example, if we think of a plane in a real coordinate space of dimension 3 R 3, this is a subspace. This makes life probably simpler, that a plane is a subspace of a 3D real coordinate space. Why? I have two vectors in that plane, these two are coplanar vectors. If we add them, the resultant if we add them, the resultant will also be a coplanar vector, or I should add it properly. Say if I add it, the resultant must lie in that particular plane, that comes from the law of vector addition or law of planarity. And if I multiply a vector with one constant, this should also lie in that particular plane. So, this plane becomes a subspace. Any vectors in a plane can be magnified, like multiplied with a particular constant or linearly combined, and the resultant is also a vector which is on that plane only. So, this becomes a subspace, that means it satisfies the requirement of a vector space. Also, it says that in a sense that we started with a restriction that the vectors lie in a particular plane and the resultant is also lying on that particular plane. So, this restriction is holding even after we have done linear combination to get the resultant. So, it is now not the large infinitely spanning 3-dimensional space, it is only a plane which at least in one dimension it cannot span anywhere. It is a, if we think of the 3-dimensional geometry, it is a plane. So, it is not going anywhere probably in this particular direction. So, we have narrowed down the space. let A be a vector in this plane, then C A is also on the subspace, and that comes from the definition of a subspace. Any vector can be in a particular subspace can be multiplied with a constant, and the resultant will, and the multiplication will should also be a member of that particular subspace. So, now if A is a vector, if this is, for example, if this is a vector in the subspace space, if I multiply it by some constant C, that will also lie in that particular subspace. Now, if what will happen if C is equal to 0? If C is equal to 0, this will be the origin, sorry. If C is equal to 0, the multiplication will come back to the origin only, or this will be a vector 0 0 0, or if we write in a column vector format, this will be written 0 0 0. So, what we call typically a 0 vector. 0 vector must lie on the same subspace. Therefore, if we call a plane to be a subspace, it must contain the 0 vector or the origin, or only a plane passing through the origin is a subspace. Any subspace has to contain origin within it, because I can multiply any vector with 0 and get the 0 vector. 0 vector must be contained within a subspace. So, if I think of a plane like this, if I think of a plane like this, this is not a subspace, because 0 vector does not lie in that particular plane. So, a subspace must contain 0 vector, which is another requirement of subspace, which it comes out from the definitions only. And this is not only subspace, any vector space must contain the 0 vector, because any vector can be multiplied with a constant 0 and we can get the origin or 0 vector. So, it has to be, any vector space has to have origin within it, and that is why real coordinate spaces are vector space, because they start from origin, origin is very much within them. So, a space containing origin can only be a subspace in R3 or in any Rn. Any space which can be called a subspace must contain origin, and this is extremely important when looking into the subspaces. So, three things we got: subspace, it is a smaller space than the vector space ideally, it must contain origin, and all these things is due to the fact that if we add two vectors, they in a subspace they must lie on the subspace. If they do not lie in the subspace, then initial two vectors we cannot call them that they were also member of the subspace, the subspace do not exist. If we say that this is a criteria, say x is greater than this, y is greater than this, I will get an xy which will be a subspace. This only will be acceptable if we add two vectors on the subspace, or if we multiply any constant with a particular vector on the subspace and the resultant lies in the same subspace. That tells us that origin has to be there. So, x is greater than 1, y is greater than 1, any vector with x y cannot be a subspace, because origin is outside it, origin is 0 0, which is less than 1 in both cases. Okay, let us go to the next slide. So, if R3 is a 3-dimensional vector space, but a plane is a 2-dimensional space. So, a subspace can have lesser dimension than the actual space, then not actual space, than the real coordinate space. Real coordinate space can be up to R infinity. A subspace can have a lesser dimension that, like here we are discussing about a real coordinate space which goes to R3, which is R3, it is a 3-dimensional real coordinate space, but the subspace what we are discussing is the plane. If we look into the slide, this subspace is the plane, and this plane is a 2D geometry. No, a plane is a 2-dimensional geometry. However, any vector in this plane must have 3 components, because it is in R3. So, this vector is a1, a2, A3 and this vector is B1, B2, B3. Though this is a two dimensional space, but the vectors have 3 components because the vectors are member of R3 or 3 dimensional real coordinate space. A subspace can have lower dimensions than the general coordinate space Rn. So, Rn R3 has is a 3 dimensional coordinate general coordinate space, 3 dimensional vector space, but the plane this particular vector space is 2 dimensional vector space. We can also think of a line passing through the origin. Any vector along this particular line, think of a line passing through the origin. So, any vector along this particular line can be added with another vector on this particular line and the resultant will be in this line. Any vector can be multiplied and the resultant will be also along this line, only thing the line has to go through origin. It becomes a subspace of R3, that a line passing through origin. However, this does not have 3 dimensions, a line has a single dimension only. So, a subspace is a smaller space within a particular vector space where the vectors have components same as which is the number of components of the vector is same as the dimension of the real coordinate space. However, the subspace may have a lesser dimension than the number of components in the vector. Like here we looked into about 2 subspaces, one is the plane which is 2 dimensional space, another is the line which is a 3 dimensional space. Which is an 1 dimensional space, and R3 is a 3 dimensional space. So, 3 dimensional real coordinate space has 1D subspace, 2D subspace, it can have a larger dimensional real coordinate space, also can have smaller dimensional subspaces. However, vector number of components in the vector is the same as the dimension of the real coordinate space. The vectors must have n components. 0 vector belongs to any vector space and subspace, and we have seen that if we multiply any vector by 0 it will be 0. So, by definition of vector space, any vector multiplied by with another vector must be a member of that vector space or the subspace. Therefore, 0 vector has to be member of the vector space or subspace. Any vector space or subspace cannot be formed bypassing the origin. And interestingly, 0 vectors may have, if we talk about R3. So, 0 vector in R3 has 3 components. This is 0 0 0, 3 components. It is different than a 0 vector in R1 or R2. It is a 3 component 0 vector because it is a member of R3. However, the dimension of 0 vector is always 0 because it is a point only, it has no length, no orientation, nothing. So, dimension of a vector and dimension of a vector space is and dimension of a subspace is different. Dimension of a real coordinate space is the number of components we need to express that vector, and that will stay with the vector if we think of a subspace also. Subspace may have lesser dimension, but the number of components in that vector must come from the fact that what is the dimension of the real coordinate space which is mother of all these subspaces. And 0 vector becomes the smallest possible subspace. 0 vector is itself a subspace. Why? If I have a in 3D I have 0 0 0, I add with another, and this belongs to a subspace. The only member of the subspace is a 0 vector. I add with one, I get zero vector only which is member of the subspace, or now I multiply a 0 vector with a 0 vector, I get the 0 vector only. So, 0 is a 0th dimensional subspace or the smallest possible subspace, and I will again iterate it because this is very important, that what is the dimension and what is the order or what are the number of components. 0 vector has 0 dimension, but the number of components comes from the fact that it is a member of R3, which real coordinate space it belong to, that says what it should be its number of components. Okay. So, we consider we will look into few examples of the subspaces. We consider a 3 by 3 matrix. Each matrix have 9 components. So, they are vectors of R9, right. 3 by 3 matrix, they have 9 components, and if I try to write a 3 by 3 matrix, we have to write 9 components. Therefore, they must be member of real coordinate space with dimension 9, because I can express a 9 dimensional vector using a 3 by 3 matrix, all the components of 3 by 3 matrix. So, this is R. So, all symmetric 3 by 3 matrices, they form a subspace in R3. Any 3 by 3 matrix is a member of R3, R9, sorry, they form a subspace of R9. Let me block it, they are a subspace of R9. Any matrix is a member, is a vector which is a member of R9. Any symmetric matrix, now we are putting a restriction over it. Any symmetric matrix is a member of a subspace of R9. So, it is not all the matrices, all the members of R9, only the symmetric matrices, that means only where 1 2 is equal to 2 1 or the second component is equal to fourth component type of vectors are members, are form a subspace. How will it be? If we see, if we linearly combine two symmetric matrices, the linear combination is also a symmetric matrix, like this is symmetric matrix, A and B, they are two symmetric matrix, and the linear combination, the 2 1 term is same as 1 2 term, the 1 3 term is same as 3 1 term, the 2 3 term is same as 3 2 term. So, the linear combination is also a symmetric matrix. So, symmetric matrices form a subspace in R9. You can add two symmetric matrices, the resultant will be a symmetric matrix. You multiply a symmetric matrix by a coefficient and the product is still a symmetric matrix. Therefore, all symmetric matrices form a subspace. Now, the question can be, and we can probably address it later, the question can be that what is the dimension of that particular subspace, right. And of course, maybe we will see it here, that in order to express a symmetric matrix, in order to express a symmetric matrix, we need 1 2 3 4 sorry not 4 1 2 3 4 5 6 terms. So, it should be a 6 dimensional space, though it is a member of R9. Anyway, we will see few more examples of a subspace. Consider all vectors in R2 whose components are non-negative. Vectors x is greater than equal to 0, y is greater than equal to 0. So, any vector in the first quadrant. So, we consider all the vectors that will belong to the first quadrant. X is greater than 0, y is greater than equal to 0. We include the origin also by writing greater than equal to 0. So, all these vectors, do they form a subspace in R2? If we multiply, say we take a vector 2 1 and then multiply it with -3 into 2 1. So, that will be -6 into -3 which is something here, which is not lying in the first quadrant. So, if I take the first quadrant, if I test that whether all vectors in first quadrant are forming a subspace in R2, no, if we can multiply a vector with a negative number and it will come out of the first quadrant. So, this cannot be a subspace. As suitable multiplier, we can get a vector in another quadrant. We can linearly combine two vectors and get multiply one with negative number and can get a vector in the third quadrant, fourth quadrant, so on. But all vectors in x y, so with y is equal to x form a subspace, and again why is it so? So, if I think of the R2 plane and this is the line I told earlier, that line passing through origin is a subspace. So, any vector, this is y is equal to x, any vector 3 3 can be multiplied with any number and that will be say 15 15, still a vector with y is equal to x. Or if I add 3 3 and 15 15, I will get 18 18, which is again has the same y is equal to x criteria. So, this criteria is satisfied when we do linear combination or multiplication or addition of vectors. The criteria satisfies here, but the criteria x greater than 0, y greater than 0 does not satisfy when we do a linear combination of the vectors in the first example. Therefore, this becomes a subspace. The second one, y is equal to x, becomes a subspace, and also it is important to see that this is passing through origin. Now, the third question, if I think of all vectors pointing to a parabola, all vector with y is equal to x squared, do they form a subspace? So, we can probably try to see. So, this is y is equal to x square. Now, I will think about any vector pointing here, say this is x and this is y. So, this is this does not become y is equal to x square, sorry. So, I will draw it again, y is equal to, so y will be more than x, y is equal to x square. So, let us assume it to be this. So, this is 2 4, a vector here which is pointing to the location 2 4, the vector is 2 I plus 4 j. Now, if I multiply this with say 3, we get 6, the resultant vector, if I thrice increase this 6 12, and we can say that this is coming out of the parabola also, y is not is equal to x square. So, or we can add 2 4 with 1 1 must be in the parabola, 1 1 somewhere here, the resultant 2 4 plus 1 1, the resultant is equal to 3 5, that is also not in the parabola, y is not is equal to x square. So, the answer is no. If we multiply a vector with another constant, or if we add two vectors, it does not satisfy y is equal to x square. Therefore, a vector x y with y is equal to x square will not be a subspace also. So, this is important that they have to go through origin, that is true. Along with going through the origin, they have to also satisfy the criteria that if we add two vectors, that will follow the same criteria through which we are defining the subspace, or if we multiply the vectors, they will follow the same criteria through which we are defining the subspace, and this criteria is not satisfied by resultant in the first and third case, where it is satisfied in the second case, and that is why this is an yes case and these two are the no cases. So, we will keep on exploring it, and now one important thing is that what are the types of subspace we can have. The subspaces will have a dimension less than the actual dimension of the actual real coordinate space of the real coordinate space, or maybe it is equal to the dimension also. See what can be the different dimensions or different subspaces in that way. For example, we can see that a line can be a subspace, right. A line passing through the origin can be a subspace in R2. A plane can be a subspace in R3, also a line can be a subspace in R3. So, what are the different types of subspaces? In R3 there can be 4 types of subspaces. R3 itself is a subspace. Anything belonging to R3, if we add it, we will get R3 a vector belonging to R3, or if we multiply it, we will get a vector in R3 only. So, R3 itself is a subspace. R3 it itself is a subspace. Any vector here, if we add or multiply, we will get here. Then the next subspace can be a plane containing the origin, and we have seen that any 2 vectors in this plane, we can add these 2 vectors, we will get another vector in that particular plane only, we can multiply this, we will get a vector in that plane only. A line passing through the origin. So, any vector along this particular line, if we add this with another vector along this particular line, this will be the resultant will be a vector on this line only, or if I multiply any vector on this line with some constant, this will be only on this line. And interestingly, the origin is which is to be noted, origin is a member or 0 vector 0 0 0 in R3, 3 zeros, a 0 vector with 3 components is a member of all the subspaces. And the fourth one, we have discussed it earlier also, is the 0 vector itself. This is also a subspace of R3. So, now I tried to demonstrate the definition of vector space and subspace, which will be very important when we will do our next discussion, which is on again our motivation behind all this thing is solving x is equal to b, which is we will start looking into the A matrix. What are the subspaces inside A matrix we can find out. We have seen that a matrix can be itself a m into nth order vector, but there are other vectors inside a matrix, and we can look it from other perspective also. If we remember the first few lectures, we have tried to write a matrix in terms of combination of matrix equation in terms of combination of column vectors. So, do these column vectors form a subspace also? We will try to look into it, and then we will see that what type of subspace or vector space is formed by the solution of the equation x is equal to 0 or x is equal to b. The solutions, what type of space do they form? This we will explore in the next few classes. Thank you.